Hello and welcome to the last part of the forecasting tutorial. My name is Tim Januszowski. I'm an applied science manager at Amazon Web Services AI Labs, and I'm based in Berlin. In this last part, I'm going to talk a little bit about forecasting systems. So basically the vehicles that allow us to bring some of those forecasting methods that we've talked about in the previous parts to the real world. What I'm going to do is to look at two extremes in how to construct forecasting systems. One of them is we take a simple model and basically lift it through layers and layers of processing steps to a real world problem. This is the mental image of the onion that we have on the left-hand side. This is one extreme, and the other extreme is instead of having a complex pipeline, we have a complex model and then relatively simple processing steps. And let me talk about the onion example first. One thing that you need to do with classical models, and an example for a classical model would be a state space models or an ARIMA model, is that you add to the signal that you have at hand. So for example, this beer time series that I'm showing you here, you add a series of pre and post processing steps before and after you forecast. So in this example here is that you first fit a linear trend to it to detrend the time series. This is the result there. Then next you deseasonalize, and then you try to forecast the remainder. And then of course, you need to then apply those steps again on top of the signal. So you need to re-seasonalize and retrend the signal. And this basically means that at the core, we have a simple model, and then we have layers of processing steps around it, each of which can be of at least the same complexity as the original model, the original forecasting model. And the example I gave you here is a quite canonical example, often called the STL decomposition. But if you think about more involved real-world examples, such as cold starts, we assume in the classical methods that we always have enough history available, but this may very well not be the case. So if we have cold starts, so no history available, what we typically need to do is to find some related or similar items with enough history and to extrapolate from them. And those finding similar items could be a very complex model in itself, maybe a clustering step. And the other example would be promotional lifts. So if you want to forecast the effect of a promotion that you've never seen before, you potentially have to independently estimate the effect of that promotion before. So you can think about this pipeline really being arbitrarily complex, consisting of arbitrarily many steps. Some pros, some advantages and disadvantages of this approach is that because we have rather simple models at each layer of the onion, this is relatively easy to understand. We're also decomposing. We're using the decomposition principle. So this means that we can decouple quite well. Each model hopefully is quite easily understandable or somewhat simple. This means that we can inspect it potentially well. We have a white box approach here. And because many of the classical models operate on a per time series level, hopefully this is embarrassingly parallel in a computational sense. However, on the flip side, what we have here is that we don't really learn end to end. So this means we have to invest a lot of manual work in modeling each step here in the pipeline, and this may be hard to tune and even harder to maintain. Because classical models are often local methods and not global methods, it's very hard to learn across time series. And this can be important in the scenarios I mentioned earlier, promotional lifts or cold starts. And this means that we have to then have a pipeline of models. Cold start I mentioned already, and then because we are in a white box setting and everything is model-based, it also means that we have to model everything. Otherwise, we won't be able to see those effects. And you may wonder why I didn't mention certain points that you would typically expect with the more classical or non-deep learning approaches. And I wanted to go through some of them. So interpretability is often used as an argument in favor of more conservatively parameterized methods. However, from a forecasting system point of view, we are really looking at the interpretability not of every single layer of the onion, but of the onion itself. So while every model, every step or every layer of the onion may be interpretable, the whole pipeline might quite likely not be interpretable. Running time may also be quite high. If we think again about this cold start use case of promotional lift, so we have to learn across different time series still there. This means that it may still take a lot of time to run, and on-demand forecasting may be actually harder to realize than one would think at the beginning. The infrastructure that we have with these simple models, that may be quite complex because we have to combine models in very sophisticated ways, and we have to stage them appropriately. So this can be quite a system challenge to build. And then other things are maintainability, that it's very hard to train those systems and to keep evolving those systems over time. One big concern that we have here is that because we're not learning end to end, but we're typically learning each layer or training each layer independently, it is not clear that if you improve a single layer, that you're improving overall performance. And it's very hard to say what is actually an important bit to get right in the onion. And because we have to stage different models in a more sophisticated pipelines, it often means that we are much less data efficient than we would think. It's because we would always need to reserve a little bit of data for validation and tuning. In general, if you wanted to build a forecasting system with classical models, there's a paper at VLDB 2017 on how to do this. Let me just highlight maybe a couple of things that we've seen here. We've got ensembling as a general component that we would typically need with the classical models, so that we make sure that we get not just a single model, but we actually get multiple models forecasting it, and then have an overall better improved accuracy. You would have standard data cleaning steps at the beginning, and feature transformations, of course, are as important to forecasting accuracy potentially as their models. One thing that I want to highlight is this top layer, this analysis layer. And this is one thing where forecasting systems may be a little bit different from other typical machine learning systems, in the sense that forecasting systems, they do not have an end-to-end and do not face the end customer, consumer, but they're typically consumed by either systems, other automated systems, or business users who then take decisions on them. So things like reporting and plotting is very important for a business intelligence user. Now, this was one example. The other examples I want to give here is with neural forecasting approaches. So how do systems look like? Well, we've got some advantages here that what you would typically need are very, very standard feature engineering techniques that can bring you that can make sure that the system is actually fairly well tuned. Because neural networks are typically employed as global methods, we naturally learn across different time series. Training may take a lot of time, but inference is quite quick. So you can also you can realize on-demand forecasting scenarios quite well. And what we've seen in the past when we've looked into productionizing some of our neural network methods is that the effect of hyperparameter tuning actually was quite limited, which if you wanted to turn it around can be something quite positive, in the sense that with default hyperparameter settings, you would get surprisingly good results. And of course, an advantage of neural forecasting methods is that they're based on neural networks, and they are currently the state of the art in terms of accuracy. So these are advantages. Some disadvantages are that naturally you're giving up control. You have a highly or over-parameterized method. What can happen is that you may face some high variance across different training runs. So you have to do some tricks like model averaging there. Yes, neural networks are still very costly to train. And because you have this explicit training step, maybe in contrast also to classical methods that are so quick in training that you can actually do training and prediction at the same time, you would need some additional infrastructure such as model serving infrastructure. However, summarizing it, in many industrial applications, neural networks are the state of the art. And this has been reflected in recent competitions. For example, Kaggle competitions on Wikipedia web page hit data, and the M4 Makridakis 4 competition that was also won by a neural network, and more completely said, a neural network with an exponential smoothing component in it. And the verdict is still out, but will happen in the M5 competition. The M5 competition is currently running on Kaggle. It's getting quite a lot of traction there. And it's going to be interesting who's going to win, which method is going to win this, and then of course, who also. But overall, I think what we can see is whenever we want to build a forecasting system, it's going to be complex. And this kind of complexity isn't something that we will really not escape. And this is what I've tried to put here as a conservation law on this slide. So the complexity is either in the pipeline, right, which you would have in a classical forecasting system. You have a simple model, but a complex pipeline setup, or in a neural forecasting system where you've got a complex model, but a rather simple pipeline. And of course, this is very, I'm putting this here for the sake of exposition primarily. Of course, the truth is somewhere in between. Right? Maybe you want to also combine classical methods with neural networks, or you want to be able to override neural networks in certain situations when the forecasts potentially go crazy. And also, one thing that I want to mention here is that neural networks, while I've used them for the sort of other extreme in my explanations, they're just one example. If you wanted to use random forests because you like them, then you probably would have very, very similar, you come to very similar conclusions. And taking a step back, of course, forecasting systems are just machine learning systems, and there's nothing too different from forecasting systems than from the general machine learning systems. So many of the components that you would have in a general, or what you would want to have in a general machine learning system, you would also have in forecasting. And a forecasting setting, with the one difference that I mentioned before, is that, let's say, different from recommendations, forecasting is not end consumer facing, but rather it's more like a business to business scenario here. And then in machine learning systems, you've got lots of components that you will need. Of course, ETL components, maybe data provenance management is important. Of course, you need some experiment tracking, model ensembling, and so on. As a whole laundry list of challenges that you need to solve when you want to build such a system. One thing that I want to call out is a consequence essentially of this B2B setting, or of the way that forecasts are consumed. So they are not consumed by the end consumer, but rather by business users or system that has basically a consequence in live testing. So yes, you would still want to do live testing with forecasting systems, But because the forecasts are not a means, are just a means to an end, but not the end in itself, A/B tests are often tricky, right? So imagine you're building forecasts for an inventory system, then you're not really interested in the goodness of your forecast itself necessarily, right? You can somewhat see that quickly or test this quickly in an A/B test, also in a live A/B test, but you're also interested in whether the buying systems are making better decisions because of your better forecast, hopefully better forecast. So these A/B tests can have a quite long turnaround time. And this is an interesting challenge, I think, that might be somewhat specific or more pronounced in forecasting systems compared to other general machine learning systems. And then there's some references here on the components that you may need and build forecast or machine learning systems. Now, if you want to get started with forecasting, I think typically you wouldn't be doing that with building a forecasting system, but rather trying out some stuff on your laptop maybe. So I wanted to go over some tools, some practical tools you have available to get started here. And the first thing to get started with, I think, is probably Rob Hindman's R package. It's called Forecast. There's a new version of it coming out also, but I think the original version is still one of the most loved and robust method out there. So this is definitely something that you should take a look at, but it comes with a caveat, and that is you have to like R. Prophet is something that is a forecast package developed by Facebook that came out is a bit more recent. It has Stan as its backend. It's quite flexible, but a bit slow also. It's something that has an R front end, but also a Python front end. And then there are other examples. TensorFlow has some time series capability built in, and then there's of course a plethora of forecasting packages or time series packages in R. And there's an overview article that we wrote in 2019 on some Python-based forecasting, open source forecasting packages. Now, I mentioned at the beginning that I'm part of Amazon Machine Learning, and I want to, of course, not spare you from a bit of marketing here. So at AWS in particular, we have quite a broad and deep set of capabilities when it comes to forecasting. So the way AWS looks at its machine learning offering is in 3 different layers. We've got the AI layers, AI service layer, where you need comparatively little data science or machine learning background. And there's an offering there called Amazon Forecast. I'll go into this later, that basically targets business or software developers. At the ML services layer, this is largely Amazon SageMaker. This is more targeted at tech-savvier customers. We've got Deep AR as a built-in algorithm. And then if you're a scientist or someone who likes to get his hands really dirty, we've got GlueOnTS at the ML frameworks and infrastructure layer. And the way we think about this stack basically is that, the further down you go, the more research oriented you become. GlueOnTS, and especially is geared towards scientists primarily, and the higher up you go, the more business oriented you are. And let me go over GlueOnTS first. GlueOnTS is Apache license. It's out there on GitHub. It's currently under review, but there's an archive manuscript available that we're pointing to here. GlueOnTS is based on MXNet, and in particular the Gluon API for it, and it comes with a plethora of forecasting models. So Deep AR is one of them. We've got deep state space models in there, Deep Factor, LSTNet. A lot of models are available. MQCNN, for example, And what is quite nice is that if you want ever have a new modeling idea, you will be able to come up with a new model, hopefully more quickly than if you started from scratch. And here are some components that we have in GluonTS. We have some components that basically take care of some heavy lifting, like object serialization and hyperparameter validation that you will need to solve at some stage when you're writing more, or when you're going to spend more time on a machine learning problem. And it also comes with a lot of time series utility methods. We have some data sets that you can access quite easily with GluonTS. There's a bunch of public data sets available for which we have loading capabilities built in, including the M5 competition. And then there's feature transformation steps that you can do that are quite flexible, and they're all part of this transform package. And then in the model, and I'll go into this a little bit deeper, is the way we define our forecasting models with the standard sort of estimator predictor interface. It's very similar to, let's say, what Spark and scikit-learn do. And then backtesting is something that is maybe a bit particular to forecasting. We talked about this earlier, where this is important also to get right. So in forecasting experimentation, so there's quite some tooling there that helps you in making this a bit easier. And then here's some examples that we have available in GluonTS. So we've got lots of metrics for computation. Metrics, of course, are something that you want to get right. You don't want to have a bug there. So having a well-tested suite of forecasting metrics out there is important. And sometimes, for example, in the continuous ranked probability score, they may not be as easy to implement. So it might be nice that something is already there. We've got lots of distributions for modeling the output. Things like negative binomial distribution, or if you want to go slightly non-parametric via splines, that's also possible. And then we've got all kinds of time series specific transformations, such as the venerable Box-Cox transformations that you can also deeply embed into your models. Now, here's an example of how easy it is to set up a forecasting model, or to run a forecasting experiment with GluonTS. So after a couple of standard imports, you can quite easily get a data set. Here in this case, it's the electricity consumption. Then you define, in this case, an estimator, the deep AR estimator, with some hyperparameters. You train it, this estimator, and then define some evaluation metrics, quantiles that are going to be interesting to you. In this case, we chose 0.1, 0.5, 0.9, but you could choose something else here. And then we evaluate this in backtest. GluonTS uses matplotlib for plotting of forecasts. Of course, metrics are great, but they can only sort of tell you a little, one part of the story. Looking at forecasts is going to be a very important step, as is for any machine learning problem. And what we have here is that we have some utility functions that allow you to plot forecasts a little bit nicer, or a little bit more easily. So in this case here, we show different quantiles, 0.1 and 0.9. And the way we assemble models, and I want to talk about this for a moment, is basically by combining it from different components. So if you think about deep AR, right, deep AR is a neural network, and RNN or LSTM consists of that component. It essentially is a stepwise rolling forward model. So it's a canonical model. And as an output distribution, it uses parameterized distributions such as student t, negative binomial, or Gaussian. On the other hand, if you take, let's say, a deep state space model, the distribution there currently is a Gaussian distribution. There's an update going to be coming out hopefully soon, where we can have normalizing flows also. It is going to deep state space models rely on state space models as the probabilistic component. Again, it's not a sequence to sequence setup, but a canonical setup. And we're going to estimate the state space model parameters with an LSTM. So this is a good way to see how the different systems are playing together here. The different components are playing together here. Fluent.AS, we launched it in summer last year. It's almost 1 year in. We're quite happy with the community traction we've seen so far. So there's a couple of additional forecasting models that came in through community efforts, something like LSTNet or NBeats. They are part of Fluent.AS now. We will have more time series applications coming in. Fluent.AS is not called Fluent Forecast, but Fluent Time Series for a reason. So we want to broaden the horizon a bit more and go into other applications that need time series analysis. We will have more model and more other components coming in. I mentioned normalizing flows as an example that is hopefully going to come in soon. And then there's some general work that we need to do on, and hopefully that the community helps us also to do to make Fluent.AS more flexible for backtesting. Of course, documentation could always be better. Okay, this was basically the ML frameworks layer. On the next layer upwards of the AWS offerings, what we have is Deep AR. It's an algorithm that was available in Fluent.AS, open source, but also in SageMaker in a slightly different version. And because it's available in SageMaker, you can take advantage of all the tooling that comes in SageMaker, so you can quickly build, train, and deploy machine learning models. And because it's fully managed, bringing this deep AR-based solution to production should be relatively straightforward. And finally, on the highest layer of the AWS machine learning stack, we've got Amazon Forecast, which allows you to really quickly generate a forecast solution with a couple of clicks. Here we take a deep learning model in 5 clicks, and then you've got a production solution up and running. So you only essentially have to set up a data pipeline. If you want to, you use auto machine learning, or you can also directly choose one of the algorithms available in Forecast, for example, an enhanced version of Deep AR. If you've ensured that the accuracy is actually with what you're expecting, you can then, in the 4th step, deploy the predictor, and then you set up in production and you can generate forecasts. Yeah, so Amazon Forecast really is forecasting as a service, allows you to set up forecasting pipeline quite rapidly, but then also to work with it and to continue to customize it as you dive deeper into your problem. So we've seen this slide before. It's the summary of the AWS offering. At the ML frameworks layer, we have Fluent.AS, then Deep AR and SageMaker, and then finally, for business-oriented users, Amazon Forecast at the top layer. And with this, we've come to the end of this tutorial. I want to thank you for your attention and want to point you to the website that we've set up for this, where you see all material, all the slides and additional material on the website. And in particular, we've you will see the references that are coming on the slides here that I will not record, but you can get them from the website. And with this, I hope you've enjoyed the tutorial. Goodbye.